Okay, so now let's do an example using the fact that the velocity is the derivative of position and acceleration is the derivative of velocity, or the second derivative of position. All right, so let's look at this example here where we're given a particle moving around with some acceleration function, given here by 4ti plus 6 sine tj plus e to the tk. Right? And then we're also given its initial velocity and its initial position. Right? What we want to do is find the general position function for any time t. Okay, so to begin this, the first thing we do, well, if acceleration is the second derivative of position, then we have to kind of undo two derivatives. So if we integrate acceleration once, we've undone one derivative, and that actually puts us in velocity. Right? So we're going to integrate the acceleration function, and that'll give us velocity. Okay, so v of t, this will be the integral of a of t dt. Okay? And this is just integrate component by component. Right? So integrate 4t, and we get 2t squared plus c1 I. Right? And remember, when we integrate the different components, we're going to get different constants of integration in each case. So it's important that we label them differently. So in this case, we're going to go c1, c2, c3. All right, so let's integrate 6 sine t. So this will be minus 6 cosine t. Sorry, let's do this. Instead of minus 6 cosine t, let's actually go plus, open a parentheses here, minus 6 cosine t, because we have to put this c2 in here times j. Right? So we may as well just sort of keep all the j things together in a set of parentheses. Right? And then we have to integrate the k component as well. So plus e to the t plus c3 k. All right. So this is, it's the velocity function, but there's a whole bunch of these unknown constants in here. So how can we take care of that? Well, this is where the initial velocity comes in. I almost said initial value, which is correct, but in this case it has a specific meaning. It's the initial velocity. Anyway, so we can use the initial velocity here to figure out what c needs to be. Right? And that's just, well, the initial velocity is at time equals 0. So let's plug t equals 0 in here. So v of 0, this is c1i. Plug in here, you get 0. Right? Over here, we get plus negative 6 plus c2 j. Okay? And plug in here, plus 1 plus c3 k. Okay? All right. And, well, that's v of 0 according to this function, but that must be equal to this up here. So this is 3j. Okay? And now we have sort of a system of equations, right? Because over here, this secretly has added on to it, there's a plus 0i and a 0k. I know those are slightly out of order from each other, but what this says is this c1i has to be equal to 0i. Right? So this will give us three things here. c1 equals 0. That's from comparing the I coefficients. Let's do the same thing for the j. Negative 6 plus c2 equals 3. Right? Compare the j components and do the same for the k. 1 plus c3 equals 0. So now we can figure out what c1, c2, and c3 need to be. Well, c1's already done, right? It's 0. Okay. C2 we get is 9. And c3 is minus 1. Right? No big deal here. So now what we do is we take these three, c1, c2, and c3, and plug it back into the velocity function we found up here. Right? So v of t is 2t squared I plus negative 6 cosine of t plus 9j, right? And then do the same thing for k. Plus e to the t plus 1 k. Okay. So now we have the general velocity function for this particle moving under this acceleration. But we're not quite done yet. There's one more step. We have to integrate this again to get the position function. And you can probably already guess, we're going to have to do the exact same thing we just did here. All right, so we've moved our velocity function up here, and we actually also corrected a typo. Our c3 was negative 1, and I had plus 1 down here, but now it's a negative 1 as it should be. So if you caught that, kudos. All right, so now we need to continue onward and integrate this one more time, and it's going to be really the exact same process. So let's do it. So the position, r of t, this is just the integral of velocity. Okay? And we just integrate term by term again, just like last time. Okay? So, oops, sorry, not plus. I don't know what I'm doing here. Equals. So we integrate 2t squared, and that's going to give us 2/3 t cubed, right? Plus, we may as well use c's again. We could change it to another letter if we wanted. But since the c's from before are gone, we can just recycle them. But you can use d, you can use k, whatever letter you like. Right? So that's our I component. Let's integrate the j component. That'll give us plus negative 6 sine of t plus 9t plus c2 j. And then integrating the k component, e to the t minus t plus c3. Okay. Okay. Well, you remember what we did last time. We have an initial value to work with, and that's how we're going to get rid of these constants again. So r of 0, plug that first into the function we found here. That gives c1i, plug it in there, plus c2j, right? Because sine of 0 is 0, and well, plugging 0 in for just t is 0. And over here, we get 1 plus c3. Okay. Right? And that's going to be the 0 vector. Right? That's our initial value here for the position. So the 0 vector, which if you remember is 0i plus 0j plus 0k. Okay. And using this, we can find c1, c2, and c3 again. Okay. This time it's pretty easy, so I'll just write down here. c1 is 0, c2 is 0, and c3 is minus 1. Right, that's just comparing them. So c1 is 0, c2 is 0, 1 plus c3 is 0, so that means c3 is minus 1. So this time we don't make a mistake when we're plugging in the c1, c2, and c3 to get that our position function, r of t. Well, this will just be 2/3 t cubed I plus, I'm going to flip these around so the one with the plus sign is in front. So 9t minus 6 sine t j. And then in here, we have e to the t minus t minus 1 k. Right? And that's our position function. So let's put a nice box around it here. Right? And that's it. So it's really just integrate, plug in your initial value, integrate again, plug in your other initial value. Right? That's all.